Okay, we should be recording now. So this is lecture 5. This is the cloud computing lecture. We did a little bit of administrative stuff, so you do have homework 0 through 2 graded now. We have at least one person who needs an extension for homework 3, so I'll show the solutions next week. Is homework 4 going well? Has everyone started? Okay. Has anyone finished? Okay. So it's definitely doable. Again, do try to start it as early as possible because especially the first half is a lot of work and time. Yep.
I just had a question about the training.
Yep.
So it says that we have trained a machine learning model, but
Yep.
I tried doing it with the what is it, SGCD or classifier.
Yep.
But is that the one we're supposed to use? Or?
You can use that or any other one. That's the one that I use because it's quick and easy, but there's hundreds of other ones you can choose from.
Okay.
Any scikit-learn model is fine.
Okay. I used the one from the logistic
That's fine.
as well.
Yep.
But then I have to import some stuff like
Yep.
define splits. Is that fine?
That's fine. So when I import a couple things from scikit-learn, that means you can use anything in scikit-learn. Okay, any other questions on homework 4? Any problems that people have encountered? No one's complained that their computer's exploded or they've got 10 terabytes of data on their computer all of a sudden?
The default value for the regressor is usually 0.0 something.
Yep.
But I found that it takes like half an hour for that to run, and I always set the tolerance to 10. Should I use a different regressor or?
Did you change the max iters?
I think it's 1,000, something like that.
Okay. So there's a couple things here. First of all, for this homework, and for basically all the homeworks in the first half of the course, you don't need to get good results. You need to show me that you know how to do it, and if you had infinite time, a powerful computer, you could eventually get there. But I'm not going to take off points because your results don't look good, as long as they look correct, if that makes sense. Like you can always train it longer to get better results. Don't care. Most of these models have some kind of max iters thing that says like, how long should I keep trying to train this for? If it plateaus, it usually does something called early stopping. I think I mentioned that before. You can stop early, that's fine. You can keep training it longer, but you're not going to get more points, so don't worry about it. I would actually switch the max iters to be even lower. I'd keep the tolerance relatively high. You do want it to learn within a certain accuracy level. But that's how I would answer that. It should never really, the first, I would say all of the homework assignments. If the homework assignment takes you more than like half an hour just to run one chunk, that's probably too long. You can probably get away with stopping it early. The final project might take you a little longer because you might have a bigger amount of data, but most of the homework assignments, I'm purposefully trying to give you a small amount of data, so it shouldn't take too long. We'll also talk more about different ways to do it. So I think the SGD classifier might have some kind of like batch size parameter. If you make that bigger, that can also be faster. So there might be ways to improve it, but don't worry about it, basically.
Last question.
Yep.
When I opened the shapefile, I found that sometimes there is nuns, a nun type,
Yep.
and also values that are at the limit of int 64.
Mm-hmm.
And I just set those to be -1. Is that fine?
Kind of.
And then class 10, like give them the class 10.
Kind of. So all of these should have some kind of none or no data. So in Eurocrop specifically, there are fields where they're not growing agriculture, or we don't know what's growing there. So urban areas just don't have any labels, or things like that. So that could be the source of none. Those you can stuff in the other, or you can ignore. Technically, it's more correct to ignore, but I haven't taught you how to do that yet. For the big numbers, if you're using those string classifiers, the EC, what is it? EC, HCAT, and whatever, some of those numbers are really big. But that doesn't mean that like they're actual numbers. They're just bigger than int 16 or int 32. So you might have to change the maximum size. I don't think it's int 64 large, but it's a big number.
I used so the EC thing is a Eurocrop, but I used the original.
The code, okay,
The codes
yeah.
there are between 0 and 900.
Yeah, so that's fine too. But yes, some of the numbers are big. If you need to, you may need to change the data type to fit them, or use a different code. That's also fine. As long as you pick a number that represents the crop type, not the field number or something like that, and there's no like big overflow or warning messages or something like that, it should be fine. Okay. I'm sure everyone will have the exact same question in about 3 hours, so thank you. Okay, any other questions on homework 4? This is, like I said, the hardest one. I promise that today's one is super easy. Don't worry. Cool. And then we also went over the feedback survey, mostly positive, a few suggestions, many of which I was already planning on improving, but some that I can definitely work on. So this is useful for me. I'll try to do this again in a few weeks. Okay, what are we going to talk about today? First of all, what is cloud computing and why and when should you use it? What cloud computing providers exist, both for compute and for storage. And then we're gonna take a huge step back for what may seem very unrelated. We're gonna talk about things like functional programming. And then we'll see why when we get to Google Earth Engine, which happens to primarily use functional programming. And at the end, I will show you this week's homework, and then I will also show you the details of the project proposal. Don't worry, it's due in over a month. Okay, so first of all, what is cloud computing? What is the cloud? So I still remember very vividly when I was kind of, I don't know, after college or so, I think that's when cloud computing started to become a new buzzword. And my parents knew that I was computer inclined, and the first thing they said is, what is the cloud? They didn't really understand the concept of the cloud. It's very ambiguous, it's very nebulous, it doesn't really have a shape or a form. So I tried to figure out how to explain to my parents what the cloud is. And I realized it's actually much simpler than other people think of it. So I have a 3-letter acronym that is my explanation of what the cloud is. It's just someone else's computer. That's all it really is. Whether you're using Google Drive or you're using Google Compute, it's really just renting space or compute on someone else's computer so that you don't have to manage the details, you don't have to manage the security, you don't have to manage the hardware or maybe even the software, and you can still get things done. So this is the short description. This is the longer description. So there's actually many different kinds of cloud computing, and there's different layers and levels of abstraction depending on how comfortable you are with cloud computing. So all the way on the left, this is the kind of traditional approach to computing. You buy your own computers. You have your own on-premises servers. You set everything up yourself. You have to pay for hardware and electricity. If the power goes out, so do your computers. If the computers are old, you need to buy new ones. If something goes wrong, it's your fault. But also, you have access to everything. You can control everything. You don't have to worry about sharing your data publicly with a different company. So there's a lot of benefits here, but it does require the most amount of personal expertise. You might have to hire people who know how to build a server and run a server if you work at a company and you want to set up your own on-premises server. The next layer of abstraction is getting rid of the hardware. So now you're saying, I would like to rent hardware, computers, storage, etc., but I still want to have control of everything on top of that, all of the software, all of the database, the operating systems. I still want the security, but I'm okay with managing the security. So this is another good choice for people who don't want to deal with buying the hardware, and we'll see some benefits of this later. The third one is platform as a service. So now you are renting both the hardware and the basic operating system, low-level stuff, but you can still write your own software on top of this. And this is basically what we're going to see today with Google Earth Engine. That one kind of fits in this bucket. So you can still develop your own applications, but you don't have to worry about things like security and databases. Those are provided for you. And then finally, software as a service. This is closer to things like Google Docs, where you can't write your own program, you can't write your own application, but you can still use it to do stuff. All the software is done for you, all the applications, operating system hardware, you don't even have to think about it. Same with Google Drive. You're not programming anything, but you're storing data there. So that's that level of abstraction. I also wanted to walk through a couple examples of what cloud computing actually looks like. So the first one I want to talk about is all of this data that you downloaded and used for homework 2 and homework 4, all of this Earth observation data. So there's an interesting paper, and this is from 2 years ago, so these numbers are out of date now. But basically at this point, there's over an exabyte of public Earth observation data, and even more if you include private data. So we have a ton of data, too much to really fit on anyone's computer, no matter how big your server is. And at the same time, it's not getting better, it's getting exponentially more. So if you just look at the number of satellites that have launched every year, we're getting up to the point where there's thousands of satellites orbiting the Earth at any time, all capturing high frequency imagery all across the Earth with higher and higher fidelity, higher resolution, and higher file size. So where do you store all this data? How does this all get managed? From this same paper, this is a nice schematic basically detailing the entire system of data collection, data processing, data transfer, data compute and storage. So I guess starting in the ground segment, you have someone in charge of actually launching the satellite, but once it's in the air, you still need a ground station to receive transmissions from it. So you're streaming all of these images down to Earth. You've got a mission control center with a bunch of people sitting there, processing the data, making sure there's no issues with it, doing things like calibration and validation. And then once you have all this data in a format that is useful, you want people to start using it. So where are you going to store that data to allow people to easily use it? There's usually some kind of a data center that you need to store these petabytes or even exabytes of data. So you have a huge data center that someone's managing. Again, it could be on premises, it could be in the cloud, both okay. The users themselves usually don't have access to that data center. Usually they need to either download the data directly to their own computer and do local computing, or some data centers will also have cloud computing attached where you don't have write access, you can't overwrite any of these files, but you can still load them quickly and easily and do processing of them. So this entire right half of this table is basically all cloud computing. Cloud computing is very, very crucial for most Earth observation segments just due to the total data volume and due to having one data provider and thousands of data users. So no one has enough room to do everything locally. You usually need to be able to process things in the cloud. This is another example that I came up with. I actually can't remember anymore if this is a real thing or I just came up with this idea. But let's say you want to build a global forest mapping system. And anyone can log in and see whether certain forests have been cut down for deforestation or planted for reforestation. So your goal is very high resolution maps of the entire Earth and where every tree is. So there's some pros of using cloud computing that can be very attractive. When you first start your website, you probably have 1, 2, 3 users. Hopefully, after a year, you've got 1, 2, 3,000 users. And depending on how popular this service is, how popular what you're building, you may need to be able to scale up to handling a lot of people visiting your website. Instead of buying 100 servers up front and praying that someone will someday use your website, you can rent 1 CPU. And if you need more, you get 2 CPUs, and then someday 3. And if your website is not as popular anymore, you can scale it back down. So you don't have to buy everything up front. You only pay for what you use. That's true for storage, that's true for compute, everything else. So that's a really big advantage of cloud computing. You can quickly scale up or down as needed depending on total number of users and how much they need. Another big benefit is security. So I'm guessing no one in here is like a cybersecurity specialist. I'm definitely not. This is not something that everyone can or should have to learn in order to make a website. So I really don't want to know the details of how people hack databases and things on my system. I just want a system that works and I can get my research to users without having to also get a PhD in cybersecurity. So that's nice. Maintenance. Someone else is also managing the hardware, not just the software. So if my server dies, I don't have to get in a car and drive to the office and fix it. I don't have to buy a new part and wait 3 weeks for it to get delivered. There's 100,000 CPUs. They can just switch me to a different one automatically, and my website's down for 5 seconds instead of 5 weeks. So these are really nice benefits. And then, of course, for any kind of system like this, you want to be able to share it with everyone around the world. So instead of setting up your own internet connection, setting up your own internet host access point that anyone can access, now you can just have this in the same AWS cluster that everyone else is using, and you can easily share data, resources, information around the world. There are obviously also cons of cloud computing that are always worth thinking about. So we said security is a pro. It's also a con. So if you're taking your data and you're putting it on someone else's computer, technically it's supposed to be private. It's supposed to be your data. In practice, the system administrators do have access to your data. They're not supposed to look at it. They probably don't usually, but they might. So if you have really sensitive information, it should not be in cloud computing. I've worked with a few people who work on, for example, nuclear energy research. And a lot of the simulations they use are really important, but also really private, really secure. And you cannot have those kind of things leak to other people, other countries. And so a lot of people who are really, really concerned about data privacy, they'll not only have everything on premise, they'll actually disconnect the whole server from the internet. So that if you want to get your code on there, you bring a thumb drive, you put it on there, and then the thumb drive gets shredded so that nothing can be taken off the system. So there are these very high security systems that are air-gapped from the internet, and they have no access at all. So if data privacy is really important to you, cloud computing can be a pro and a con. The other thing, and this is more of a personal opinion, but maybe you would agree, I find a lot of the cloud computing stuff to be very difficult to get into. There's just so much terminology and options available out there. Everything has a different name. Instead of folders and directories and files, you have blobs and buckets and all these other terms that basically mean the same thing, but they came up with a new term for it anyway. So I find it to have a pretty high learning curve, but it is worth doing and it is quite useful for certain applications. So let's look at some of the people that provide cloud services and what you can use them for. And this is what I mean by too many options sometimes. So these are really the big three providers, I would say. There's others out there as well, but Amazon with AWS, Microsoft with Azure, and Google with GCP. These are the three biggest and most common cloud providers. And each of them have many different options available to you depending on how much control you want or how much abstraction you want. So again, you can either do something where you basically run all of your own software, operating system, everything, all the way on the right, down to these no-code, low-code interfaces where you basically don't write anything, you just drag around some boxes and you get results out. So Amazon EC2 is really popular with a lot of people I talk to, but Kubernetes is a little bit easier if you just want to scale things up quickly, all the way down to things like Lambda, where when someone clicks a button, it runs a program and then it stops. It's not persistent. There's no memory or storage or anything else. It's just, I want to run this function, do it. Yeah. Power BI is another common Microsoft Azure service. It's basically just Excel in the cloud, but more powerful. They also have their own virtual machines and containers. And then Google, we'll talk about Google Earth Engine today. That would probably be somewhere in the middle where you can still write your own code, but you don't have to deal with the operating system or the data or the hardware or anything else. So there's a lot of options available. It depends on how much control you want versus how much you don't want to have to think about. We talked about this very briefly in lecture 2 when we talked about where to find data. There is a lot of data in cloud providers, including those big 3 that I just mentioned. So I want to quickly go to some of these websites to show you what I mean. So this is Earth on AWS. AWS has a ton of Earth observation data available that you can use. And no, I don't want to talk to AI. So I can look at all of these geospatial data sets available on AWS. You can see things like Sentinel-2 or Landsat. So all of the same data that you're downloading from USGS Earth Explorer or Copernicus Dataspace, it's already in the cloud. On these websites, you don't need to download anything. You can actually do the computations directly where the data is without having to wait for transfer. You can also download the data from here directly to your computer and do the processing there. And there's pros and cons of that versus the USGS or ESA systems. So there's Sentinel-2, there's Landsat. This is GOES, so this is meteorology. They have cloud optimized geotiffs. I think I mentioned that a little bit. Worldwide energy data, terrain information such as elevation, slope. NextRad is all weather radar. I think I was talking to someone about this yesterday, and there's like over a petabyte of data just for the US in here. So there's a ton of data in NextRad. Ice velocity and elevation, if you're interested in glaciology stuff. ESA World Cover is a land cover mapping product for the whole Earth. Polar satellites. SpaceNet is a data set that's used for competitions for things like building detection or road detection, etc. So there's a ton of different things here for many different applications, both raw satellite imagery inputs as well as predicted outputs or even machine learning ready data sets. So when you're thinking about your final project, where to find data, this is one of the many places that you should look. And you can, of course, search by any key terms you want. This is the Microsoft Planetary Computer thing. So this is actually a lot more recent. This is one of the newer ones, but they already have a ton of data available here as well. So this is really popular, this harmonized Landsat and Sentinel. Basically, they take all Landsat data, all Sentinel data. They try to map one to the other so that you have twice as much images of the same kind for the whole Earth. So this is quite widely used, but they have all the older individual Landsat products, MODIS. Here's the answer to one of the questions earlier, where do I download non-optical imagery? Here's some Sentinel-1 data, Sentinel-2, but also Sentinel-3 for aerosol, Sentinel-5P, also for air quality. I actually worked in this specific group when I was at Microsoft Research. So they built these little low-cost air quality sensors and deployed them around cities and collected air pollution data at like a block-to-block city level. And all that data is up here as well. So if you're doing air pollution research, they've got that. Things for biodiversity, both labeled images taken from camera traps, but also larger observation records from citizen scientists. A bunch of biomass related things if you're trying to measure the amount of biomass that could be a carbon sink. No, there's more, it's just gotta load, there it is. Yeah, that's all the biomass. Yep. Climate data, so I don't think this is, yeah, this is either CMIP6 or related to CMIP6, but this is global climate predictions from different climate models. Just for the US, This is all of the weather forecasts that the ECMWF makes. Yep.
Is sort of this data free, or there's some limitations on usage, or?
I think it's all free. There's usually limits, like there's usually limits of you can't download too much too quickly. So there's usually these kind of like usage quotas, but it's all free. They often also have private data that you have to pay for, but I think all these ones are free. ERA5 is a global reanalysis product for weather, so that one's really useful for a lot of different applications. Fire detection, I've had a bunch of people work on wildfire detection projects. Hydrology. Yep. Okay, we can just scroll through here. Elevation stuff, demographics, fire, infrastructure, land use, land cover, synthetic aperture radar. They've got a whole section for that. There it is. Pulsar, Sentinel-1, Sentinel-3. Snow, I've had people work on snow detection. Soils are really important for agriculture, solar potential, temperature, water, etc. So there's a lot of different data available on here. It's mostly free. There used to be a Microsoft Planetary Computer Hub where you could actually log in, set up your Jupyter notebook, and directly access all the data. Unfortunately, that was discontinued. But all the data is still there. You just have to download it to your system or set up your own thing on Azure to process it. And then the third one on my list is Google Earth Engine. This is the one we're going to spend the most time on today. So this one's been around for a very long time and it has a lot of data, and it also brings the compute together, so it's really convenient. They've got a ton of different data sets here. You can see the common ones like Landsat or Sentinel are right at the top, but there's a lot more data sets in total for things like climate and weather. Let me go back, it's too much. A lot of things for climate and weather, raw imagery, including high resolution imagery, but this is only for the US, but I think they've got some other high resolution image sources for other places as well. Geophysical stuff like elevation, terrain, land cover, agriculture. So there's a ton of different data sets here. And I'll talk about that a little bit more towards the end of the lecture. Let's see, where am I? Okay. The other thing is not just for the people producing the data or sharing the data, but also for you as students and researchers. You can also upload your own data or your own code in cloud services. So one of the more common ones is GitHub. So I wanted to show an example of one project here. So this is the TorchGeo GitHub repository. You can see all the code here. And the important thing is that multiple different people can work on this code and develop it together. So it's kind of like Google Docs where multiple people can edit the same document at a time, except you have to suggest something and one of the people who owns it has to approve it. But otherwise it's the same thing. So I actually talked to Tomb Legal about this. They had questions about some GitHub stuff I was doing, and they asked me, what is GitHub? And it was so hard to explain GitHub, but the Google Drive and Google Docs analogy is the closest thing I could think of. So this is a great way to share code. And then Hugging Face is another common website where you can share things like data or models. So here's a bunch of data sets available for agriculture, biomass. I believe this one is meteorology and weather, land cover mapping, flooding, etc. And you can find even more. So we don't get to talk about TorchGeo until the end of the course, but if you're looking for data sets, this library has more data sets than everyone else combined. So there's like 130 data sets here for both like raw geospatial products, but also some of these curated ML-ready benchmark data sets where there's both inputs and outputs that you can train models on. So there's audio data here, there's high resolution, tree plantations, Sentinel-1 and 2, LiDAR data, Maxar high resolution imagery, Sentinel-1, Terrace-RX. This is for glaciology. This is for wildfire. This is for cloud cover detection. So this is also a really good place to look for data sets for your final project. Okay. The other question is not just cloud storage, but also cloud compute. So now you know where to get your data from. You know where the data already exists. Where do you run your code? At this point in the course, everything that we've done runs fine on your laptop. It's not that big of a data set. It's not that slow. When we get to deep learning next week, it's going to become much more important to have access to a good GPU. Some laptops have a perfectly decent GPU, some don't. There are free GPUs in the cloud that you can use, especially for homework assignments like this. So there's two main products I want to share, and I'll have my own personal opinions on them. One is Google Colab. So this is basically Jupyter Notebook in the cloud. You can connect it to your Google Drive, and you can access your data sets from Google Drive. You can run things in the cloud relatively quick, like there's a timeout if you run something for more than half an hour, they might kick you off. So there are, again, usage quotas, but it's really, really easy to use, really easy to get started. It's the same thing as your current Jupyter Notebook setup, but now it's running on someone else's computer instead of your own. So I'll show this in a second. I like Google Colab because it's been around for a very long time. It's not likely to go away anytime soon. It's very simple and easy to use. It has that nice Jupyter Notebook interface, and you can connect it to your Google Drive. The other one that's more recent is this Lightning Studios platform. So this is made by the same developers as PyTorch Lightning and Torchmetrics and some of the other software libraries that we're going to see later in the course. This is similar to Google Colab. It's a competitor, but it takes a very, very different stance. So with Lightning Studio, it's a much more powerful system, but as a result, it's more complicated. So there's more options, there's more knobs that you can use to control. One of the biggest and most important things with Lightning Studios is it gives you less abstraction and more control. So previously you only had access to a Jupyter Notebook, that's all you could do. Now you can have an entire storage connected to your compute. You can have persistent software installations, so you don't need to reinstall your software every time. You install it once and it just continues to work for as long as you own it. And you can also put your data on there and not worry about it being deleted at the end of the day. You can use it through a Jupyter Notebook interface, but you can also directly connect VS Code or even run the terminal and run command line tools in Lightning Studios. So it's much more powerful, but as a result, it's more complicated. So I wanted to briefly show what these look like. So this is Google Colab. When you first get here, you can either upload a notebook, or you can grab one from Google Drive, or you can grab an example notebook and play around with it. I can, for example, create a new one. Doesn't usually take this long. There it goes. Okay. This is just a random Jupyter Notebook. It automatically saves to Google Drive, so I don't have to worry about this disappearing. And I can run any code I want in this cell. So I can type import sys, print sys.platform. And I can run it. It first has to connect to the CPU. And I am on Linux now. So this is a Linux server in the cloud, and I can run any Python code I want on it. And it also has access, at the moment, it doesn't have any access to a GPU. So if I run this magic command, it should say command not found. Yep, cool. If I go up here to the top right corner, and maybe make this a little bigger for you. If I go up to the top here, there's a bunch of information about the resources I have access to. At the moment, I'm not really using much of the storage or the RAM here. There's different connection options. So I can connect to a hosted runtime, which means I have my own server, but I want to use the same environment. But I can also change the runtime type. You can do Python or R or Julia here, but we do Python in this course. By default, you're connected to a free CPU. You can use as many as you want of these. Google doesn't really care. I can also connect to a GPU. And this is not a good GPU, this is an old GPU, but I'm just on the free tier, so that's what I get. But this is more than enough to do your homework assignments for the course. You can also play around with the TPU if you want to run code on there, but we'll talk about that later. But for now, let's connect to this GPU. So I will save and I will connect. So now I'm in a new environment. If I run this again, I should still be on Linux, but now I have access to a Tesla T4 GPU. It's got, what is this, 16 gigabytes of RAMs? That's actually decent. It's not too old. Current usage is 0%, so I've got it all to myself. Great. So now I have a GPU that I can run all the later deep learning stuff on quickly and easily in the cloud. So this is relatively simple, easy to use. Other stuff that I should show off. You can upload the homework notebooks that I give you. You can also download those notebooks. Those are the download options. There's one other important thing I want to show you. Another really important debugging tool that I probably should have said earlier, in a Jupyter Notebook, if anything goes wrong and you don't know why, restart session and run all. Just clear all the memory and try to run it again from scratch, and you will very quickly realize, like, you ran this cell, but then you deleted it, and the variable still exists, and that's why you're confused, or you ran this cell twice, and now the variable's been updated twice. So this solves a lot of problems. We already saw change runtime type. Settings I want to show you. So as you remember, no GPT, no AI assistance. You can disable this. Otherwise, it starts recommending, would you like to hit tab to complete to solve the whole homework assignment? So you can delete all of these features so that it doesn't connect to Gemini automatically and it doesn't use them for your homework assignment. So this is really useful, very recommended, because that's not allowed. But otherwise, this is pretty simple, pretty straightforward. You know, you have a few other options in here with style and things like that. You can upgrade and you get a certain amount of services. Apparently, we can get Colab Pro for free as students and educators. I didn't know that. I might have to get that tonight. So yes, this is very, very useful for your homework assignment. It's a free GPU, and you get 100 compute units per month. I don't know what that is in hours per GPU, but it depends on the type of GPU. There's also Colab Pro. That looks expensive. You should not need to pay any money to take this course. Don't buy any textbooks. Don't pay for any deep learning services. You can if you want, but I'm never going to make you. Okay. You can also connect to GitHub, which is cool. I have absolutely no idea what Corgi mode is. Nothing. Oh, there it is. A very useful feature that someone spent hours coding. So there's Corgi mode. But otherwise, this is basically just a Jupyter Notebook. Plus, you get to choose if it's a CPU or a GPU. That's about it. Everything that we've done up until now has been mostly CPU only. You can technically run scikit-learn on a GPU, but you have to install like another CuPy plugin or something like that to get that. But for now, it's not really that slow. When we get to the deep learning models, oh, there's a different dog now. When we get to the deep learning models, you definitely want a GPU. So this is a good place to start. How do I disable this? Okay. The other one I mentioned is Lightning Studios. So this is the Lightning AI platform. I was actually looking at this the other day, and fun fact, that little picture in the top here, I actually made this when I was a grad student. And I don't know how it ended up on this website because I never contributed to the website. It was just like a little demo thing that I wrote for some code. And then I think they made it their own demo using it and borrowed the image. But that was kind of cool to see on the front page of the website. But yeah, this is a pretty popular service. It's relatively new. This came out a year and a half ago. And they're still kind of building it up. But the nice thing is that you can have your own studio, your own development toolbox, including storage, GPUs that you can connect. It's all flexible. You can pay as you go, as needed. You can have persistent storage. So once you install things with pip or conda, you don't have to touch it again. And it continues to work and it's reproducible. So there's a lot better reproducibility here. You can do batch jobs just like you would do on a computing cluster. If you want to run the same code 10 different times with 10 different hyperparameters at once, you can do that. You can do like a simple training workflow, but then you can also do inference and deploy it on services for users if you want to set up a small company. There's these cool environments. So these are basically demos where people said, here's how to set up a reinforcement learning tool to play arcade games. Or here's how to deploy a large language model in practice, or fine-tune this for stock market prediction, or stuff like that. So these are little blog posts with code that you can run directly in Lightning Studio. They have a bunch of models such as Llama, DeepSeek, GPT-5, etc. These are all available to use directly in the cloud, and you can deploy them and set up a chatbot or something for your company. Here's the documentation. This is my homepage, so I can set up my own little projects here. I can manage my compute. I can add a new cluster and scale it up. Some old random test things that I set up. Never done deployment or pipelines. Yeah, I haven't used this very much, but I've been meaning to for a very long time because it is much better than Google Colab. It's just much more complicated. So those are the two that I recommend. There's many more out there. You don't have to stick to these, but if you don't have access to a GPU, now you do. We're about halfway, so I think this is a good time for a break. Maybe let's meet back at 4:20 and then finish. And then we'll go over Google Earth Engine and the homework in the project report.
I just have one more question that
Yep.
popped into my head. When I downloaded the data from Zenodo, whatever, I found that band 10 is always missing.
Yep.
Is that normal?
Yeah.
Okay.
So Zenodo has the Eurocrops.
Yeah.
The imagery is from ESA Data
Yeah.
Space, whatever. Yeah. So there's level 1 and level 2 products.
Yeah.
Level 1 is just the image taken by the satellite plus some geocorrection. Level 2 is removing the atmospheric distortion.
Mm-hmm.
The band 10 that you're missing is completely useless for surface
okay.
reflectance. It's more for calibration and for cloud detection and for things like that. So that's why it's not in the level 2. So you can ignore that one. You can skip that. It's fine.
Okay, because my code, it looks fine.
Yeah.
But I was just thinking maybe there's a little date or something.
Yeah, that's why.
Okay, great. Thank you.
About this third one, is
Yep.
it like because like merge the band files into like the run order?
Yes.
Okay. Okay.
Yep. Yeah, it's 2, 3, 4 instead of 4, 3, 2. So
Oh.
4 is red.
Oh, that's
Yeah.
why.
That's why all the colors look weird. A lot of
Yeah.
people made the exact same mistake. Don't worry.
Okay. Thank you.
Yep.
also when we run this command, can we actually rename the bands?
Yeah.
Does it appear in QGIS? Because in QGIS it always shows band 1, band 2, band 3, so it's somewhat confusing to.
That's a good question, actually. I don't know if you can change the number. You can change the, I think by default it says grayscale band 1. You can change that to like red, green, blue and force it to say like, oh, now I know that it's this red, green, blue format. But I think it keeps the bands in ordinal numbers. You could also merge all 12 bands, which is what you do for homework 4. And then they're going to be in the right order. But even then, Sentinel-2 has band 8 and band 8A. So there's really no way to keep them in the same order. So you just kind of have to keep track of which one is which, unfortunately.
Is it okay if I turn on the lights?
Yeah, go ahead. As long as we can still see the front. I remember I used to teach an 8 a.m. course during the winter semester, and it was really depressing because even by the time the course ended, it was still dark outside. I hated that course. I can't wake up early.
Sometimes we have days where we start at night, all the way through the day, and end at night.
Yep. It's one of the biggest differences I noticed moving from the US is like the weather's the same. It's just as cold in the US, but Germany's just such farther north that the days are much shorter.
I spent one semester in Iceland. It was even worse because it was the winter semester.
Oh, that's dark.
Yeah, with 4, like, I think one thing was just the daily hours of sunlight, but the bad thing was even if it was supposed to be sunny, with these low pressure areas, so it was always rainy, it was always cloudy. So I think in total I saw the sun for maybe a day, like 4 months. So
How long were you there?
like 4 months about. Yeah, I wouldn't recommend. Summertime is better.
Yeah. I had a friend who was in astronomy, and she actually got to go to the South Pole to work on the South Pole telescope. And she was there during the summer, so it was 24 hours of sun. But there's also people that are stuck there over the winter where it's no sun for 4 or 5 months, even if there's no clouds. It's a cool experience. It's something I want to try at least once. It's not something I want to do for the rest of my life, though.
Yeah, I think it's an interesting experience.
Yeah.
But it really, I think, place you have to use vitamins and get everything together because otherwise it can be very depressing.
You realize how little control you have over the world when, like, the things just change so much with the seasons. I can't imagine being someplace like California where it's just always the same temperature, always the same sun, always perfect. You have no idea which day of the year it is. It just seems boring.
I guess in the South Pole you get to learn to love the moon.
Yeah.
Do you even get to see the moon yet?
Yeah.
Ah, okay.
Yeah, I think you can. But Southern Hemisphere is all completely different constellations. I think most people have returned. We can restart now, so we don't end up being too late and you get home before it gets too dark. Yeah, so I mentioned this before. I want to take a huge step back and talk about programming languages, and you'll see why later, I promise. So the point of this next few slides is there's actually many different ways of doing the same thing. So there's many different programming paradigms. So what you've seen, probably the only thing you've ever seen, falls under the name imperative programming. So this is where you have code that runs in order, and there's memory, there's state. You process steps one at a time. A code snippet like x equals x plus 1 makes perfect sense. X was 5, now it's 6. That's okay. I actually, the first time I TA'd CS 101, I had a math major student, and he saw this, x equals x plus 1. He was like, how is that possible? And I had to explain that, like, it looks like math, but it's not math. It's actually stateful memory. Things can change over time, which is not really how math works. This student would have loved declarative programming, where there is no state. All you do is declare the answer, and it runs it. And there are no steps involved. It's a single chain. So this is closer to something like x plus 1. There's no state. I can't save that for later. I just have a function, and I run it, and there is an output, and there's no step-by-step process. We're going to talk about this today. The other two are not as common. So symbolic programming, this is where you manipulate equations and formulas. You can actually do this in Python. So Python is 95% imperative. It's actually 5% declarative, and we'll see that today. Python itself doesn't have symbolic programming, but there are Python libraries like SymPy that you can install and import, and you can take things like the integral of an equation, and it can calculate that for you. Everything so far in this course has been imperative. Today is going to be declarative, and then everything after today is actually going to be differentiable. So when we get to PyTorch, all of a sudden we're manipulating formulas that can be automatically differentiated. You can take the gradient of your model automatically. So that's the entire second half of the course. And importantly, programming languages like Python or libraries like PyTorch or SymPy, they can support one or more of these programming paradigms. So no language is 100% one of these little buckets. What does this look like? What are some more detailed examples? So looking at imperative programming, this is most programming languages that you've heard of, things like C, C++, MATLAB, Python, Java. These are all imperative languages. It's common because it's simple and it's easy to understand, and it makes sense, at least for the people who wrote many of the first programming languages. There's two types of imperative programming languages. The first one is procedural. So you write a function or a method or a procedure, and you run it. And that's it. That's a way of collecting code in one bucket, but there's no other higher level abstractions. So for example, in Python, this might look like numpy.reshape. That's a function, we can reuse it. Here's our two inputs, do the thing, give me the output, nothing else. Python is actually more closely aligned with object-oriented programming languages. So now we're not only defining functions, we're also defining new data structures and attaching functions to them. So for instance, I can actually take X, which is an array, and I can directly reshape this array using this array method that is attached to the object. Similarly, with matplotlib, I can get the axis, and then I can run all of the functions that are allowed on that axis. So this is a way of organizing the code with the data, as opposed to just a set of functions where you have to check which data types are valid. So that's imperative programming. You've seen this before. This should be relatively straightforward. What we're focusing on today, which is different, is this idea of declarative programming. So now, instead of defining how to compute something step by step, we're just saying what the answer actually is. So the one that we're going to focus on specifically is called functional programming. This is common in languages like Lisp or OCaml or Haskell. Basically, in these languages, everything is a function, and all you have are functions. So Python can actually do a little bit of functional programming. This is an example of a similar syntax where instead of saying for x in sequence 1, indentation for y in sequence 2, execute these things one at a time, one after another, we can just say, make these lists, make these tuples from everything, and just write the answer directly without doing a step-by-step computation. And then Python can actually go in and say, oh, I know what you mean. I will remove all the state. I'll make this code run faster, but the syntax is a little bit uglier. So Python can actually do a little bit of functional programming. I'll show more examples later. The second one is logic-based languages. So this is actually one of the earliest forms of AI. A lot of the AI research in the 50s and 60s was rule-based and fact-based. If I know certain information, if I can declare certain rules, can I determine the correct and only correct answer? So for instance, I can set up, I can define what a parent is. I can define a grandparent as a parent of a parent. And if I have these kind of rules, I can ask it questions like, is A related to B? Or is C an ancestor of D? I can set up all kinds of rules, facts, and query it for correct answers using this. So that's Prolog. That's still used in some things. I use this for concretization of software libraries, but you don't need to know what that means. And then the last one here, this is a little bit less common. This is reactive programming. Here you're, instead of working with variables that have a value, you're actually working with data streams. And anytime you change one thing, it changes everything else. You've actually seen this before in Excel. So in a language like, I think this might be reactive or Elm, if I say A equals B plus C, and then I change the value of B, A would also change. So that's how it works in Excel. If you have a formula in Excel and you change one of the inputs, it changes everything else throughout the whole table. So these are all forms of declarative programming. The one I want you to focus on today is functional programming. So the core concept from functional programming, the reason why we're introducing this in the first place, is because of this map, filter, reduce paradigm. So these are three really powerful commands that allow you to scale up anything that you ever need to do with very little code. So there's three commands. The first one is map. It turns out there's a lot of times when you have a bunch of things and you want to run a function on everything. So this is called map. Run the same function on every element in a list or a tuple. You might also want to filter out some of the elements from that list that don't apply. So this is called filter. And then the third one is reduce. Now we've got a list. We would like to squash it into one dimension. Can we add everything, subtract everything, multiply everything? These are all ways to reduce the data in the list. Python actually supports all of these if you know where to look. So let's say I have a list, 1, 2, 3, 4. These are all strings. I can run the built-in map function that you probably didn't even realize existed. I can use int, which automatically casts something to an integer, and I can map every element of A through this function to get an output list B that is 1, 2, 3, 4 as integers. Then let's say I define my own function that's greater than 2. I could filter this list to only contain 3 and 4. And then finally, I could apply the add operator to reduce the list by adding everything up to get one total in the end. So basically, if you can write your code in this fashion, this opens up a lot of opportunities. Previously, when we saw for loops, you would run things one step at a time, and by the end, you would be finished. If I guarantee that there is no state involved, I can run all of these things at the same time. So I can take my map and I can say I have 20 data points and 20 cores on my CPU, do them all at the same time, and then get my result instantly. So this is a very powerful way to scale things up. Why are we discussing this? It turns out this is exactly what Google Earth Engine uses for all of their computations. And I'll show you examples of that in a second. So I'm gonna jump over to Google Earth Engine. There we go. This is the main homepage. There's a bunch of important things to look from here. One of the important ones is this code editor. So again, Google Earth Engine not only has its own data, but it also has its own compute setup. So I can write code here in JavaScript and directly access the data available on Google Earth Engine and manipulate it and display it on this map. For the homework assignment, you'll be doing this exact same thing in Python, but there's also a JavaScript interface that I'll talk about briefly. There's a few important things here. So there's a bunch of example scripts if you want to deal with a collection of images and how to work with them, a single image and how to process it. There's documentation on every built-in function that you can directly access here without going to a different website. And then if there's any data sets that you want to use that don't exist in Google Earth Engine, you can upload them and use them in Google Earth Engine, which is really powerful. If I go back to the home page, we already saw the data sets. There's a bunch of them, but let's take a specific one and investigate it. So let's look at Sentinel. Let's look at a Sentinel-2 image, and we'll look at the surface reflectance. So for each of these data sets available, there's thousands of them. No, I don't want an AI summary. Date back from 2017 until today, provided by ESA. You can load it into your notebook or code editor using image collection and then the specific path to the data. Revisits every 5 days. There's a description about the data processing and all of the things that are done, the scale of it, different bands and what they're for. So here's all the bands that are available. You can see the original resolution of each band, the wavelength of each band, the description, what it's called, what it's referred to. These are bands 1 through 12 that you've seen before. This is all the extra metadata that might be useful. So QA60 is the cloud mask. If you want to learn more about this, you can expand this. So it's stored in uint12, I guess, maybe. So the different bits there, it's not integers. You actually have to use bit operations, but you can see which pixels are cloud, which pixels are cirrus or thin cloud, and which pixels are clear. So that's useful. Different colors that you could represent different classes as. So there's labels for these different types of surfaces. Image properties. So this is all of the metadata associated with this, what this means, what it's useful for. And then in terms of use, I'll talk about this later. What I also want to show you is this. So this is how to play around with the data. So this is the JavaScript version. This is the Python version. I'll just do the JavaScript version quickly because I can open it directly in this web interface. Here's my code. I can run this code. And what it does is it selects mostly cloud-free images for a location on Earth. So I've got a function here which does cloud masking. It looks at band 60, QA60. It checks for clouds and cirrus clouds using these 2 bits. Bitwise and dot equals dot and. So this is a composition of functions. This is a common property of functional programming. Here we have our data set. it's an image collection from here. We first filter. That's one of the map filter reduce paradigms. We can filter again, and then we can map our cloud masking function over the top. And then finally, we visualize everything in RGB. We're only visualizing these 3 bands in this order with this range. And then I can zoom in to any given location and see what it looks like. You can see it's relatively blurry. It's 10 meters per pixel. But you also have coverage of the entire Earth. This appears to be in India. Yep.
This is actually Mexico.
Yeah, cool. So I can pick any place I want to, and I can zoom in, and it will dynamically run this same code for the location I'm looking at. So I don't have to run this script for the entire Earth. I can only run it for one location at a time. If I zoom out, it's still running that same script, but it's running it at a lower resolution. So it's very flexible, it's dynamic, and it can scale up to the whole Earth very quickly at some resolution or another as needed. Okay. Other stuff I should show. Let's see, what time is it? Maybe let's save it at that for now. So Google Earth Engine is not only a source of data, it's also a source of compute. It has a very powerful API that lets you scale up across distributed nodes, and everything is this map filter reduce paradigm. Okay, back to the slides. So here are a bunch of good resources to learn more about Google Earth Engine. You'll be using it for your homework, so these are worth spending a little bit of time on. The guides I find very useful. These are like high level, if you're working with an image collection, these are examples of things that you might want to work with. The API docs are the more traditional, if you know what function you want to use, but you don't know how it works, you can read those. This last one, this intro to the Python API, this is the most useful thing for your homework assignment. So this will tell you all the basic steps to get started. And the last one is the code platform that I showed you. So I want to talk about some of the pros and cons of Google Earth Engine, what it's good for, what it's not good for, when you should use it, when you should not use it. And again, these are all my personal opinions, but they're semi-backed up by other people online who say the same thing. So I'm not just shouting at the darkness. The pros, obviously, we've got hundreds of free data sets for Earth science. So everything from meteorology to land cover, to elevation, geophysical, gravity data, etc. Most of the data sets that you might want to work with, they already exist here. And if there's one that's missing, you can upload your own. So it's very flexible, very powerful platform. This is the thing that I was kind of hinting at, but didn't explain how they do it. If you write your Google Earth Engine code in the JavaScript API or the Python API, that code, that request, gets sent to the server. That code is compiled into Java, and then that code is automatically distributed across hundreds of CPUs and run at the same time. And you don't need to get a PhD in CS to know how to write distributed code well. It's all done automatically for you just by running simple Python or JavaScript code. So as long as you follow this built-in map filter reduce paradigm, you automatically get distributed training, distributed inference very quickly and easily. The other half of this is you'll notice that the code that we just looked at did not involve reprojection. It did not involve resampling. I didn't have to think about target aligned pixels or anything else. All of that is all automatically done for me. So that's also very powerful. A lot of the things that you're currently struggling with on Homework 4, those problems go away when you start using Google Earth Engine. So I want you to struggle with it first to know how important this is. And then when you do this homework assignment, you find it's so much nicer not have to do this manually. So those are the pros. There's also a lot of cons of Google Earth Engine compared to other platforms. Again, like most of these, it's free-ish. So it's free for non-commercial, non-production use. If you're just doing research or you're a student, you can use it for anything you want. If you want to use this as someone working at a company, then you have to pay the money for the same things you used to have access to. There's relatively strict usage quotas, so you can't just download a lot of data quickly. You have to download a small amount of data at a time, and there's limits on how often you can hit the API. So you might find that downloading large images or uploading large images is slow and painful. And this is the most important one to me. It's not really extensible. So you have to use their JavaScript or Python API. You can't import NumPy, you can't import pandas, you can't import matplotlib. Those don't work on the system. Those can't be automatically parallelized. They don't work at all. So that's really tricky. What that means is you can't import PyTorch or TensorFlow or anything like that. So Google Earth Engine is amazing for simple classical machine learning, but if you want to do deep learning, it doesn't really work yet. Another thing that you're going to find very quickly on the homework, it's incredibly painful to debug some of the stuff on the homework. You have to redesign your way of thinking and doing in terms of this map filter reduce paradigm. And this works for a lot of applications. There's a lot of things where you just want to apply the same function to the whole Earth or every image in a sequence, but there's also a lot of things where that doesn't make sense. And you will find that there are certain things that can't be done in Google Earth Engine, no matter how clever you are. And the other thing is it's not really open source. So the platform itself, the code behind the system, like the features built in, that's not open source. You can't see how these are implemented behind the scenes, how they're translated to Java, where there might be bugs. You can't add new features yourself. You can only write functions using mapfilterReduce. Also, the data that's available on Google Earth Engine, even if it once was public domain free access data, all of a sudden it is copyrighted Google data. You can still use it for free, but you have to cite us as the source of your data. So a lot of people are uncomfortable with how they treat public domain data as well. These are just pros and cons. The other thing I should mention is if you want an open source version of Google Earth Engine, there's an OpenEO project that is basically trying to do the same thing that has various pros and cons. I haven't used it though, so I don't want to talk too much about it. But if you want open source version, check out OpenEO. The other important question with all of these technologies is when should you use it or why should you use it? So I want to start with who should use it. Again, I think it's better for Earth observation experts than for AI experts, mostly because you can do anything you want to in Earth observation, but you can't really do deep learning in here. So if you really want to control and experiment with different fancy AI methods, it's not perfect. But if you don't know AI very well and you want to quickly get results, this is a great way to get them. I also think it's better for researchers and educators who get it for free than it is for industry who has to pay for it. I think that's obvious. Another question is when should you use it? So there's many different styles of usage. One is just to only use it for the data. So it's got a bunch of data there, download it, and then do all of the processing locally. So this is a perfectly valid approach. You can even combine pre-processing. So for example, if you want to take your data set of all Sentinel-2 images, pre-process it to remove clouds, compute NDVI, and then download a mosaic. You can do all of that pre-processing in the cloud quickly and easily and scalably without having to worry about that on your system with GDAL and all the pre-processing steps you're currently going through. If you want to do classical ML and especially time series analysis, Google Earth Engine is great. And another thing that I use it a lot for is just prototyping. So if I have a cool idea and I just want to see how hard it is to do, I'll quickly write a simple script in Google Earth Engine and see if it works. And if it does, then I'll download a bunch of data and rewrite it in PyTorch and make it more advanced. And then the other thing is how to access it. So when I first taught this course, I did this whole lecture and homework assignment with JavaScript. And you had to learn a little bit of JavaScript to use the Google Earth Engine code editor. And then last couple semesters, I made it optional. You could either do it in JavaScript or Python. This semester, I'd prefer you to use Python, and then you don't have to learn another programming language to do it. But both APIs are basically identical. It's not hard to do it in either one. If you do it in JavaScript, you can do it directly in that code editor, so it's a little bit faster to prototype. You can easily visualize the data directly in that code editor. When you look up documentation or Stack Overflow or anything, you usually get the JavaScript version, so you might have to change a little bit to get to Python. And if you want to set up like a web application, then JavaScript is your language for that. Python, because you're mixing your own code locally and the Google Earth Engine code that gets run on the server, you can actually do a little bit more powerful data analysis. So you can directly access the server and stream the data and then do deep learning and the Python bits, but those don't get run on Google Earth Compute. Those get run on your own system. So this is more like a back-end tool that you can use instead of the front end. Okay, wrapping up, this is the documentation that I find most useful. You have the API docs for individual functions. The guides are also really useful, but this Intro to Python API will get you much farther, so I would definitely start with that one. If you want to learn more about Google Earth Engine and how it's designed and how it does these kind of JavaScript to Java translation and distributed training, the paper is actually really interesting and worth reading. So they published a paper on it, and it's got like 10,000 or 20,000 citations. So it's quite widely used in research. I'll show you the homework in a second. It's this time series nighttime cloud masking section. And then we'll talk about the project proposal. And then starting next week, we'll be doing deep learning. So let's go to the homework first. This is homework 5. Make this bigger. So homework 5, we're using Google Earth Engine. As usual, this is your Jupyter Notebook. You can run it locally, or you can run it on Google Colab if you want. That's fine too. So what are we doing? We are looking at nighttime lights. So you can not only use satellite imagery during the day, you can also use satellite imagery at night. Nighttime lights are really useful proxy for a lot of different things. So you can get quick measurements of population, migration, electrification, but also CO2 emissions, and also natural disasters. If you see that all these lights are out, there's probably a flood or earthquake in that region. So we're going to do time series analysis with this operational line scan system, blah, 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 published by these people. Again, these are the things you're allowed to use, anything in Google Earth Engine. And then there's also this GEE map tool that lets you quickly do the same mapping thing that you would normally do in JavaScript. Now you can do it in your Jupyter Notebook as well. First, you actually need to make an account for Google Earth Engine, and you need to log into that account. So there's some guides here that help you do that. We're going to load this data set, filter it to a specific range of dates, and then select a specific band of interest. So if I go to this data set, you can see it here. It's all the way back from 1992 to 2014. We can just click this button, or maybe click the same button for, oh, they don't have a Python version. That's okay. It's almost identical syntax in Python. But if I quickly run this, you can see what the data set looks like. And you can zoom in. I forget what the resolution of this is. Oh, it's kind of blurry. But you can zoom into cities and see which ones have brighter light than others. The first step is visualizing it in grayscale. Guess what? We're basically already done here. There's a little bit you need to change, for example, filtering the dates and selecting the right band. But it should be obvious how to do that. Where are we? Okay. So first do a grayscale visualization and plot it on a map. Oh, no, that's the mapping function. Okay, yeah, sorry. So first authenticate, then filter your data set down to a certain time range and a certain band. visualize it in grayscale, center the map over Munich with a certain zoom level. All of this is explained in the tutorials and guides for Google Earth Engine. And then we've already done our filter. Next is our map. We want to create a new band. For every image in our image collection, we want to get the year of that image, the date. Number of years since 1993, the start of our collection. So we're going to design a function, and we're going to map that function over all of our images. And then finally, we're going to reduce. We're going to do linear regression to fit each pixel in the data set to see if the nighttime lights are increasing, decreasing, or staying constant. This is the hardest part. This is visualization in RGB. So the goal here, and I'm not going to give you too many hints as to how to do this, the goal here is to create a single RGB image representing this data set. So places where you have increasing lights, positive slope, those should be mapped to red. Places where you have decreasing slope, decreasing nighttime lights will be blue. And then things that are relatively stable or high intensity, these will be mapped to green. And these are some visualization parameters for your range of values for red or green or blue. So the goal is to make, I don't know if I have a quick, I don't want to show you the solution, but basically you will get a pretty picture of Europe that shows you which cities or which countries have more light than they used to, less light than they used to, or are staying the same.
Does that mean that the image should only have red, blue, or green colors? Or
You can blend them too. Yep. So some places are increasing more than others, or have high intensity, but are slightly increasing.
but I mean, if they have high intensity and they're increasing, do we set them to be blue and red, for example? So we get orange or whatever.
Yeah, so that's fine. So basically, when you plot, you're gonna make your own RGB image, and the red layer is just the positive slope areas. The green layer is the intensity, the concentration, the y-intercept, and then the blue channel, that's going to be the decreasing slope areas. So you're going to merge these, and the colors can merge and combine and create new colors, yes. But it mostly looks red, green, and blue when you're done. Yeah. So this is a little tricky. Let me know if you need any more hints for that. Once you have this map, then all of the rest is just analysis. So looking at the map, which countries or cities have increasing, decreasing, or stable light intensities. I also want you to think about which steps Google Earth Engine is doing for you automatically. Not in general, but specifically on this homework assignment for the code you're doing. What does Google Earth Engine do for you, such as distributed processing or any pre-processing that you think it's doing behind the scenes? So think about that. We talked about this in lecture, but just kind of repeat from my notes or from your experience or from Stack Overflow. What are the pros and cons of Python versus JavaScript? And then what are 3 limitations of Google Earth Engine? Again, mostly just copying from lecture. So hopefully you can see this homework is quite easy. These 3 are basically just copying from notes. This is analysis, and this is just map, filter, reduce. So it's not too bad, but it's a completely new environment. It's a new way of writing code. So it might take you a lot of time to debug and read through guides and tutorials to figure out how to do it. And then the extra credit, I couldn't think of an easy way to extend this, so the extra credit's kind of different. But using the same Google Earth Engine platform, you're going to make plots that kind of look like this, looking at sea surface temperature, specifically for El Nino and La Nina. So you pick any sea surface temperature data set you want, look up dates for the most recent El Nino and La Nina events, create maps of sea surface temperature during these 2 things. They should kind of look like this. Pick a location off the coast where the temperature changes a lot between El Nino and La Nina. So for example, somewhere like this, where it's bright red here and bright blue here. you can actually do plotting and create charts directly in Google Earth Engine. So make one of sea surface temperature and then label events on the chart. Okay, any questions on the homework before we get to the project? That's the part people are more interested in. Okay, if there's any other questions on the homework, just email me. Now the project. Okay, let me zoom in a little bit. So this is up on Moodle now. You can download the same PDF as me. So the goal of the final project for this course is really to let you take the things that you've learned from lecture and go further with less restrictions. So you can pick any kind of project you want to do and explore any kind of techniques that we've learned in lecture with your data, including things that we didn't learn in lecture. I've actually had several students in this course who had a successful project in this course that ended up being a poster at a conference that they talked about later. Or you could even develop it into like a 4-page workshop paper and submit it to a real conference if it goes well. So the goal is actually to do something that's maybe not like full research paper level research, but like preliminary proof of concept working research with real data, with real problems. You can do an individual project or a group project with up to 2 people. If you do a group project, basically both of you just submit the same proposal, but put both of your names on it so I know that you're a group. That way, if one of you forgets to upload it, you still both get credit for it. Technically, you're not supposed to use a project you're already using for another course or for your master's thesis, but you can find something that's kind of related to the research you want to do, but otherwise wouldn't have time to do. Timeline, so basically the project proposal is due in January, in a little over a month, so you still have a lot of time to think about it. There's no other homework assignment due that week, which is why I chose that week. The midterm report will be a little more than a month after that, after all the other homeworks have been finished, and then the final report is more than a month after that as well. So I want to give you plenty of time to work on this. That's why the current homework assignment and all the other homework assignments later are going to be easier than the ones that you've seen so far. So I want to get you started on this and have as much time as possible because it is a lot of work.
When will the last homework assignment be?
2 weeks after lecture 10 or so. So I think like a week or 2 before this.
So like lecture 10 is the last time you announced the homework.
Yeah. I could have one for like the reproducibility or the software, but it's hard. So I'll just let you have more time to work on the final project. Yeah. Okay, the grades, you can see it in the syllabus. The project proposal and the midterm report are both worth 20%. The final report's worth 60%. And then the whole project is a 40% of the total course grade. Why are we doing this kind of multi-stage thing? I want to force you to get started early, but also I want to be able to give you feedback before it's too late and you've gone the wrong direction. So you'll get feedback immediately on your proposed idea, and then you can get started. And then the midterm report, you can tell me, I've got some preliminary results, but this doesn't work, please help, and I will help. And then your final report, you'll have a chance to get everything working and do all the experiments you want to do. This is also important. So the first 2, project proposal and midterm report, they're kind of just graded on like a checklist, like did you do the things I asked for? The final report is graded on a few different dimensions, specifically breadth and depth. So I want you to do a little bit of something from most lectures. So a little bit of pre-processing, a little bit of classical machine learning, a little bit of fancy deep learning. As long as you do something from most lectures, you get full credit for breadth. For depth, the goal is actually to do something a little bit beyond what I covered in lecture. So maybe I talk about these common computer vision architectures, but you try a different one that I didn't cover in lecture that you think might work better because you read a paper and someone said this one's useful. So that's where depth comes in. So the only reason I bring this up now is it is useful to think about how you can combine things that you learn from different lectures for the final project. I've had people who just did like a simple classical AI thing and didn't use any machine learning or deep learning, and they didn't get a very good grade on the breadth. So that's why I bring this up now. Okay, so what is the project proposal specifically? The project proposal, you're of course proposing what you want to do for your final project. I want you to be creative here and think about something that not everyone else is going to be doing. So like I've had like 20 people do urban heat island effect mapping, and it's boring at this point. But pick something that you're passionate about, that you find interesting, maybe a problem that's affected you personally or people from your hometown, flooding, earthquakes, wildfire, etc. You can pick any project that's at the intersection of AI and Earth observation. Obviously, if it's something that can be done with machine learning or deep learning, you get more points for breadth. If it's something that's related to satellite imagery, you might get more points for breadth as well. But technically, it doesn't have to be those things. So I've had people do other kinds of projects as well. Pick any topic of your interest. Also, we're only halfway through the course, so I want you to focus on what you want to solve, not how you want to solve it. We haven't even talked about deep learning yet. Don't worry about which model you're going to use or how you're going to train it. Worry about what problem you're going to solve. Also, I put this every semester and people always skip this. It's in bold. 1 page. I just want a 1-page summary of what you're thinking about doing, what data is available, etc. Don't want 10 pages. I will take off points if you give me multiple pages, just 1 page. Writing succinctly is a really important skill. So what I want to know is basically answers to these 10 questions. You don't have to do any fancy formatting for the project proposal. You can literally just do a bulleted list 1 through 10 and a couple sentences for every one. It doesn't have to be fancy. So what are you interested in? Are you interested in agriculture, natural disasters, renewable energy, oceanography, whatever? Which application domain are you interested in? What are you trying to solve? Why is it important? So a couple sentences of motivation like air pollution is the #1 cause of death in urban environments. Here are some example numbers from the UN, blah, blah, blah. What are you trying to investigate? So this could be something like, I think AI can be used to interpolate air pollution data or make super resolve imagery to zoom in to get higher resolution, or it can be used for time series analysis to detect building damage or whatever. What is your minimum viable product, expected goal, and stretch goal? So your minimum viable product, that's like worst case scenario, at least I got this working thing. Expected goal is what you think you can realistically do. And then stretch goal is if it turns out to be easier than you expected, this is the next step. And I'll give you comments on this and tell you, like, just so you know, this is way harder than you think it is. So maybe change this. Or I'll say, actually, this is pretty easy and it's been done before. Maybe try adding this. So I'll give you feedback on that. This is really important. What work has already been done before? So I know that not all of you have research experience. What I typically use for this is Google Scholar. Google Scholar is a Google search engine specifically for research papers. So let's say I'm working on, what's an example project? Anyone have any ideas yet?
Wildfire?
Okay, wildfire. We'll say wildfire forecasting, so not just mapping, but predicting it ahead of time using machine learning. And there's 25,000 results. This is actually usually sorted quite well, like the first 10 are much better than the last 10. So parameter flexible wildfire prediction using machine learning techniques, forward and inverse modeling. Predictive model of wildfires, new data set, that's useful, machine learning approach. Review paper, these are very useful for getting in a quick idea of the whole ecosystem and everything that people have done at least before 2020. Machine learning and deep learning for wildfire spread prediction. So this is given an existing wildfire, where is it going to go next? Daily wildfire forecasting, deep learning, fire risk. So there's a lot of research on this topic. We want to try to find something slightly novel. So maybe we're using a different data source than other people. We're using a different model architecture than other people. Now the second step is one that students miss quite often. The next step is to read the paper. So you can click on one of these and read it. Most of these you can access through Tomb. If you have trouble accessing it, let me know. But you can read the paper. Usually I read the abstract first, and then I decide if this is actually relevant to me or if this is something different than what I thought it was. If it's different, skip it. If it's relevant, keep reading. Introduction is useful for finding a lot of the background information. Sometimes there's also a related work section, and that's also a good source of good papers. Some of these will introduce a lot of math. You can also just pretend this is PCA. I don't care about the details of how it works. Convolutions, we're going to talk about those later. So a lot of this is going to be confusing, not very familiar. We also have k-nearest neighbors for regression. We've seen that before. Inverse problem, blah, blah, blah. Here's a algorithm for doing the inverse model. So this one's a little bit more math heavy, a little bit more research focused. You can also see some example results here. Time series predictions. PCA versus CIE versus SVD. K-nearest neighbors versus random forest versus MLP. We've already seen k-nearest neighbors and random forest. We're going to see MLP next week. So read the paper and see. You can also see, like, they'll include citations here. So this is how to cite data. The other thing that students struggle with is how to write like a bibliography of references. There's a really cool feature here. You click this cite button and it generates it for you for MLA, APA, Chicago, whatever. Don't care what you use. You can even generate the BibTeX file if you use LaTeX. So this is how I find papers. This is how I generate citations and put them in my paper. So now you know how to do that. You have no excuse to not do that. So I want you to read at least 3 papers, describe them, tell me what they're doing, how they're doing it, and then add a bibliography at the end with at least 3 citations. You can have more if you want, that's fine. A lot of people just give me a list of paper URLs. That doesn't mean that you read them, that doesn't mean you understand them. So both descriptions and bibliography. And this is important for understanding, like, are you reinventing the wheel or is this actually novel? The other really important thing that I want to know is what data is available for solving this problem. So let's say we're doing wildfire mapping. You are going to find that there's a ton of imagery, Landsat, Sentinel-2, whatever you want to use. There's a lot fewer labels. So in order to learn, you need example labels. So you need to find, preferably, someone has already labeled a bunch of images for you, which pixels are wildfire and which aren't. There's different sources out there. Some of them are just people used machine learning or AI and made a label. And that's not as good as like a human label that's 100% correct or close to 100% correct. So really, really spend some time on what has already been done and what data sets are available. Preferably, you will find existing ML-ready data sets. So for the example of wildfire prediction, there's the Chabud and Kabuar data sets in TorchGeo that you can use. But these already have a bunch of chopped up images and output labels for every image. That will save you a ton of time. If you can't find this ML-ready data set, you basically have to do the same thing you're currently doing for homework 4. And if you've started homework 4, you know how painful that is. So if you don't find labels, I will tell you, like, this might not be a good project to work on. You might want to switch to a different project where there are labels. I have had students in this course who made their own labels, And it is possible, but it's very time consuming. Okay, so find preferably multiple data sets, include like a plot of what the data looks like. You will often find that the data does not look as good as you think it does if you just look at an example image. How large are the data sets? So like how many images are there? How many labels do these images have? Like if you're doing object detection, how many planes are there in your high resolution imagery? How many pixels, etc. So just to give me an idea of, is this data set big enough to do deep learning on? Are there labels, or do you need to collect your own? If you need to collect your own, it's very painful. So try really hard to find labels. We're not going to get to dataset licenses until the reproducibility lecture, but it is important to think about the license the data is available under. It's pretty hard to find data that you can't use for research purposes, but there's a lot of data that can't be used for commercial purposes, etc. So that's good to think about. And then finally, are there any ethical concerns? The answer is almost always yes. No matter what you're trying to do, there is someone who could use your results for harm. So always think about that. It's completely fine to say yes. I could be doing wildfire prediction, and my model is really inaccurate in certain environments, and people there might be affected if this model is deployed and used in production, and it doesn't work well for them. So the answer to this is almost always yes. Just brainstorm ways that your model could be used for bad things. Okay. Blah, blah, blah. Also, the last thing I want to say is you can change your mind later. So if you find that your idea sounds really cool, and I took a look at it and I said, like, this has already been done like 100 times, it's very easy, or you just don't have the data that you need to do it. It's completely fine to change your mind and do something else later. You can change your mind at any point. You can also do like, the midterm report doesn't go well, you couldn't get the data that you thought you could download, so you have to do something else instead. That's fine. So don't stress too much, but I do want to get you thinking early. I do want to get you dreaming and envisioning what kind of project you want to solve for this. Are there any questions about the final project? Usually there's a bunch. If you have any preliminary ideas and you want to run them past me, let me know. I can say like, oh yeah, that's a good idea. There's a couple data sets I know of. Or if you have no idea what you want to do and you want me to just give you ideas, I can give you ideas. But I would prefer it that you come up with some cool idea. Otherwise it's boring and I only see things that I know too much about. All right, if there's no other questions, we can end here. And I'll stick around and answer questions on homeworks or